This is the electromagnetic spectrum. If we take a look here, we have longer wavelengths. If you take a look up here on top, the wavelengths look longer from peak to peak. And then if you take a look here, as we go to the right, the wavelengths are shorter from peak to peak or trough to trough. And we take a look over here. So AM waves, radio waves are the longest of the waves in the electromagnetic spectrum. And then the next shorter ones would be infrared. And then we have the small band here, the visible light spectrum. And then we have UV rays, X-rays, and then gamma rays have the shortest wavelengths. And if we take a look here, if we spread this out, what we have here on the visible spectrum, red has the longest wavelengths, around 700 to 750 nanometers. And then violet and blue have around 400 to 450 nanometers. And so those would be the shortest wavelengths. Now, if we take a look here, the longer wavelength is on the left side of this diagram here. So the longer the wavelength, the shorter the frequency. That means more waves pass through a certain point in a certain period of time. And then also there's less energy in these waves because they have a shorter frequency or a lower frequency. Now over here on the right side, the shorter the wavelength, the greater the frequency will be because the more waves will pass through a certain point in a certain amount of time. And then those waves have more energy. And so those waves are more destructive, like gamma rays and X-rays have the power or have the ability to cause cell damage, destruction. They have a lot of energy that are in there. Now let's take a look at a few calculations relating to wavelength, frequency, and energy right now. Here I'll draw a wave. Like I mentioned before previously, over here we have the top of a wave, and that top of a wave is called a crest. The bottom of a wave is called a trough. And in the middle, these are called nodes. And so if I wanted to find the wavelength is represented by a Greek letter named lambda, which looks like a backwards person. And if I go from one point on a wave to the same point on the next wave, that distance would be equal to the wavelength, or lambda. So the same thing would happen if I went from trough to trough. If I went from here to here, the wavelength should be exactly the same. Now let's take a look at a different wave, different drawing. Now if we take a look here, the wavelength on the bottom wave would be represented by, say if I went from crest to crest, from here to here, or from trough to trough, here to here, or node to the same node on the next wave, or any point on the wave and the same point on the next wave. So those would be the lambdas. Now, if we take a look here, like I mentioned before in the previous part of the video, so this is obvious. This should be a longer wavelength that we have here. So this is a longer wavelength relative to the one that I drew on the bottom. The one on the bottom would have a shorter wavelength. Now, if we take a look here, then we take a look at the frequency. Well, the frequency is defined as the number of waves that pass through a certain point in a certain amount of time. So it's per time. So if we take a look here, if this was a snapshot of time, we would have two waves passing through this snapshot of time. Now, if we look at the waves that I drew on the bottom, they have a shorter wavelength. In this snapshot of time, the same amount of time, 4 waves pass through that certain amount of time. So this would have a lower frequency relative to the waves I drew on the bottom. And then this would have a greater frequency if we're comparing. Now, frequency is represented by the Greek letter nu, which looks like a squiggly V. So nu. If it's not old, it's new. All right. And then the last thing is then, since there's a lower frequency, then comparing the two waves or the two drawings, this would have a lower energy than compared to this one. So this would have a higher amount of relative energy. And now let's take a look at some equations to help us figure out the relationship. The first equation we're going to take a look at is the relationship between wavelength and frequency. So C equals lambda times nu. The C stands for the speed of light. And the speed of light is a constant. And so that's equal to 3 times 10 to the 8th meters per second. So that's how fast light travels. This, like we mentioned before, is lambda, which is the wavelength. And to match the units of the speed of light, the wavelength should be in meters, okay, because it's meters per second. And then the frequency, just to make sure, since we're multiplying wavelength times frequency equals the speed of light, the frequency would be measured in 1/seconds. Or seconds to the negative first is the same thing as inverse seconds. Or hertz, like the rental car company. No product placement intended. So if we multiply the wavelength times the frequency, we can get the speed of light. Or if we wanted to isolate for one of these, all we would do is rearrange the equation. So if I wanted to calculate the frequency, then I would take nu equals, and I would divide both sides by the lambda, or the wavelength. So nu equals c over lambda. Now if we take a look here, as one's on the top, the other one's on the bottom in the proportion, or they're on the same side up here. So as wavelength goes up, the frequency goes down. So they are inversely proportional, like we had seen before. So the longer the wavelength, the shorter the frequency, or the lower the frequency is going to be, and then vice versa. So wavelength and frequency are inversely proportional, like we had seen in the first part of the slide. So let's do a little plug and chug just to practice. Okay, with a little plug and chug, let's say we have violet light that we're given, and say we have violet light is at 400 nanometers. We want to figure out what the frequency is of the violet light. So what we need to do is we just need to plug and chug. So if we want the frequency, we can rearrange these. So nu equals c over lambda. All right, the c is the speed of light. So like we talked about before, 3 times 10 to the 8th meters per second. And then we need the wavelength. We need it in meters. So since we have nanometers, remember nanometers is, nano means 10 to the negative 9th. So basically this would be equal to 400 times 10 to the negative 9th meters if we're converting. And then we can get 4.00 times 10 to the negative 7th meters. Okay, because we just converted the nanometers to meters. So make sure you have it in meters. So then we put this over here. So 4.00 times 10 to the negative 7th meters. And then the units that cancel out, the meters cancel out. And then we're left with the frequency equals. And then if we do the math, then we end up with 7.50 times 10 to the 14th, 1/seconds, or seconds to the negative first power, or hertz. So this would be the frequency of a photon of violet light. Now what we can do is we can take this, and now we can go into the relationship between frequency and energy. So now that I've written it over here, so let's go ahead and take this. So the energy equals, and then H times nu. So E is the energy, and that's measured in joules. H is Planck's constant, named for Max Planck. And Planck's constant is equal to 6.626 times 10 to the negative 34th joules times seconds. And then this is the frequency, like we mentioned before, nu. And then that's measured in 1/seconds, or seconds to the negative first power, or hertz. And if you take a look here, if we multiply these, then the seconds will cancel out, because seconds times 1/seconds, those will cancel out. Now, if we take a look here, energy and the frequency now are on opposite sides of the equation. So energy and frequency are directly proportional. So with a greater frequency, we would have a greater amount of energy. So all we would have to do to plug and chug then to calculate the energy of one photon of violet light is we would just multiply Planck's constant times the frequency, and then we would get the answer. Now, one other thing I wanted to do was, I'm not going to plug in here, but is just to show from before, we had C equals lambda times nu. Now, if we wanted to get the relationship between the wavelength and the energy, we could actually combine these two equations to figure out that relationship. And so I'm going to solve for nu here. So nu equals c over lambda. And all we did was we divided both sides by lambda. And now if I take this frequency and I substitute it with c over lambda, that's how in the textbook you end up with E equals hc over lambda, where I just substituted in for nu, I substituted c over lambda. And now from here you can tell that if the wavelength is on the bottom and energy is over here, that means that energy and the wavelength should be inversely proportional. Just like how we saw before that wavelength and frequency were inversely proportional also. So this is another way of calculating it, and you can plug and chug Planck's constant, which we have here. C is the speed of light, 3 times 10 to the 8th meters per second, and then the lambda is the wavelength in meters, and then you can calculate the joules. And so those are the three equations that would be helpful for you for this part in determining with waves and the frequency or the energy that those waves contain. Now let's finish off with the photoelectric effect. The photoelectric effect was discovered in 1905 by Albert Einstein. So he took these waves, and so he took light in general. So he took visible light. You could use UV, or you could use X-rays also. And so he took light and he shined it at a metal surface. And if there was enough energy in these waves of light, then electrons got ejected. Now these waves of light that you have here are called photons, which are packets of light that you have here. And if the photon had enough energy, and when it hit the metal surface, if there was enough energy, the electrons would be ejected, and that's what he discovered. And so you need enough energy to eject the electrons. And so we'll take a look at this next week when we take a look at photoelectron spectroscopy to figure out what electrons are being ejected and if there's enough energy to eject those electrons. So this brings us to one of my favorite memes about the photoelectric effect and photons. A photon checks into a hotel and is asked if he needs any help with his luggage. The photon says, "No thanks, I'm traveling light." Thank you so much. We'll take a look at photoelectron spectroscopy next week.